For experiment 7, we'll be talking about Torricelli theorem. We are from Group 2 and I'm Zhen Hui, and we have Anis, Intan, Haris, and Melvin. For report summary, Torricelli's theorem is a theorem in fluid dynamics which states that the velocity of the fluid, V, leaking out through an orifice at the bottom of the bottle filled to the depth of h. The law expresses that the speed of efflux, V, a liquid through a sharp edge opening at the base of a tank filled to a profundity, h, is equivalent to the speed that a body for this situation, a drop of water would obtain in falling uninhibitably from a height of h. We can assume that this experiment can be used to verify Torricelli's relationship by comparing measured and theoretical value of the velocity. This can be calculated using the equation 1, where g is the acceleration due to gravity. The equation can be derived using Bernoulli's principle. As for this experiment, to get the V experimental, we are using the equation of equation 2 or equation 3.
Okay, now I will be explaining the theory of this experiment. The Torricelli's theorem states that the speed V of a liquid flowing under the force of gravity out of an opening in a tank of proportional to the square root of the vertical distance h between the liquid surface, the center of the opening, and to the square root of twice the acceleration caused by the gravity 2g, which can be concluded that V equals to the square root of 2gh. The speed of a portion of water flowing through an opening in a tank is the same as the speed that will be attained by a drop of water falling freely under the force of gravity alone through the same distance h. The speed of efflux is independent of the direction of the flow at the point of the opening. The speed is given by this equation, whether the opening is directed upward, downward, or horizontally. Next slide shows that the figure 1, the relationship between the fluid depth and the fluid velocity. The pressure increases as the depth decreases, which results the bottom hole ejects the strongest pressure, while the above hole ejects the weakest pressure due to the depth. A container filled with fluid with small holes at the bottom of the container causes the fluid to lift through the hole with the velocity same as it would experience if it dropped from the same height to the hole level. If the fluid is dropped from a height, it will have velocity, and this velocity is the same velocity at which the fluid leaves the hole when the height of fluid h is the same as fluid drop in the container. Okay, now we'll be discussing the formula that we're going to use in this experiment. First, we can simply derive the Torricelli equation from the Bernoulli equations that we studied in secondary school. Bernoulli equation that's stated in slide. According to the theorem of the Torricelli, the fluid inside the tank known as an ideal liquid. So the fluid is incompressible. The net force of friction is also insignificant. This is why the exposure of the tank to atmospheric pressure P1 and P2 can be neglected due to its large opening. The velocity of point 1 can be negligible too, and the gravity is fixed to be in the same right and left side. The Torricelli theorem is hence obtained. Torricelli theorem describes the velocity of a non-viscous fluid from a cylindrical tank if you have fluid standing at the depth of h in an open tank whose side walls are vertical as depicted in previous figure with a hole created in one of the walls. The relation can be written as V theoretical equals to the square root of 2gh, labeled as equation 1. The equation 2 states that the velocity of the fluid flowing from the hole is the same as the velocity of a single fluid droplet falling from the height of the container surface of the liquid. In the horizontal direction, the water stream from the hole can be represented by a kinematic equation. X equals to V times t. Next, for the constant acceleration, the equations becomes dx equals to x initial minus x output equals to the v initial times with delta t plus half of acceleration times delta t squared. That will be labeled as equation 3, where acceleration is 9.8 meters per second squared. At the initial point of v equals to 0, the equation 3 can be written as dx equals to half a delta t squared. That is labeled as equation 4. last but not least, the volume V can be calculated using the following equations. And the volume flow rate too. Volume V, capital V, is equals to the A H W. The value of H is the volume of cylinder, while the volume flow rate is equals to the area times width square root of 2GHW. That will be labeled as equation 5 and equation 6 respectively. Next, we'll be discussing about the apparatus that will be conducted in the experiment. It's only 3 apparatus that you're going to use: a cylindrical cylinder with drill hole, measuring tape, and clay marker.
Okay, I will present about methodology for this experiment. First, the apparatus was set up based on 3 different stages of height. Second, the water was filled into cylindrical tank. Third, the hole at cylindrical tank were covered using finger when filling it with water, stopping filling water at desired volume of water. Then the finger was removed from the hole. After that, the maximum distance of stream was marked by using clay and the time was recorded. And then the procedure was repeated by using different volume of water and different stage of height. And the last, the result were recorded.
Now I will discuss the result and discussion for this experiment. Okay, table 1 is the result obtained from the height from the nozzle to the ground, where the height is 0.36 meter. The data that we're going to record is the volume of water, the height of water from the hole of the nozzle to the surface, maximum horizontal distance travel, average maximum horizontal distance travel, drainage time, average drainage time, theoretical velocity, average measurement experiment velocity, and percentage error. For the maximum horizontal distance travel data, we're going to record 3 different readings. Where the 3 different readings, we're going to use it to calculate the average maximum horizontal distance travel to get the more accurate data. Same as the drainage time, we also gonna take 3 different readings and calculate for the average drainage time. By that, we can use these both data to calculate the theoretical velocity and average measurement experimental velocity. After getting that, we can calculate the percentage error. Yeah, this is table 2, where the height is 0.56 meter, and the data that we're going to record is same as table 1. And this is table 3, and then the height for table 3 is 0.76 meter. Now we enter the discussion part. For the first question is, explain your selection on dependent, independent, and constant variable. For the dependent variable, I have chosen 2 variables with it. The first variable is the maximum horizontal distance travel. The second variable is the drainage time. For the independent variable, I also choose 2 variables, which is the volume of water, and the second variable is the height from the nozzle to the ground. And for the constant variable, same as the two other variables, I also chosen 2, which the first is the density of water, and the second variable is diameter of cylindrical cylinder and nozzle. Well, the reason for the selection of this variable is to accomplish the objective of this experiment, where to verify the Torricelli relation by comparing measure and theoretical value of the velocity, where this will be used to measure the effect of the height of the water on the velocity of the water, and also the effect of the height from the nozzle to the ground on the speed of the water. I think that's it for me. Thank you.
Okay, now I will tell about the discussion. For the discussion 2, the law of Torricelli can be derived from Bernoulli principle and refer to the velocity of fluid leaving an aperture in a fluid field jar to the head of the fluid above the orifice. The Torricelli law is obtained from the Bernoulli equation by equating the potential energy in the static head of liquid with the kinetic energy that exits the water through the orifice. The equation is shown as below. As you can see, P1 over rho g plus V2 V squared over 2g plus z and equal to P2 over rho g plus V2 over 2g plus z2. Okay, next, when P1 and P2 are both 0 due to the air pressure, the velocity at point 1 is considered to be 0. This is because the fluid acceleration is so modest and almost nil. Since the point issues the data, so Z2 is 0. So this the formula you guys can see at the below. Okay, now let's continue a little bit for discussion 2. After we rearranging the velocity, we get the equation like this. V2 equal square root 2 gz. So V2 is equal to square root 2 gh, where h is a theta of z. Okay, now let's move on to the discussion part 3. Okay, the experiment based on Torricelli theorem can be done in a few different ways, but only a few strategies, however, will provide a precise and reliable finding as time goes on. In that instance, the percentage relative error between the theoretical and measured value is determined to determine the precision of the experiment method. Based on the equation below, we can see is P equal to V theory minus V measured equal to V theory times 100. Okay, next, theoretical velocity, which is VTO, of flowing fluid relies on the gravity constant, which is denoted as G, and the height difference, which is h, between the center of orifice and fluid at the specific level of reservoir. As you can see, V theory equal to square root 2GH.
So for discussion number 3, we need to calculate the percentage of relative error for the theoretical and measured, which is experimental values. So this is the formula that we use to calculate the percentage error. So to calculate the percentage error, theoretical velocity is minus with measured velocity and divided by theoretical velocity, then multiply by 100%. And then we calculate the average percentage error by using this formula, which is sum of percentage error divided by 5. Okay, for the first height is 0.36 meter. The total of percentage error that we cut is 47.12, and then the average percentage error is equal to 9.42%. Then for the second height is 0.56 meter. The total of percentage error is equal to 124.57, and then the average percentage error is equal to 24.91%. And then for the third height is equal to 0.76 meter. So the total of percentage error is equal to 221.04, and then the average percentage error is equal to 44.21%.
In discussion 4, we will be talking about source of error and method to minimize the error. There are some source of error occurred while this experiment was carried out. Firstly, the leakage occurs while covering the hole in a cylindrical tank. In addition, the measuring tape should not be positioned perpendicular to the cylinder borehole. Thirdly, the time taken is inaccurate since the observer may start or stop the stopwatch too early or too late. Last but not least, parallax error occurs due to the position of the observer's eye, which is not in line with the reading scale. Several methods should be practiced to minimize the errors occurred during the experiment. To avoid the leakage, one can use a tape or stopper to be more secure. Next, the location of measuring tape has to be set perpendicular to the tank hole at the bottom of the cylindrical cylinder. Then, the experiment should repeat in order to get the average value. This will help us to get a more accurate result. Thus, the eye of observer must be perpendicular to the scale. This method will help to lower the percentage of error obtained from the results as well as polish up the experimental data. In conclusion, this experiment can be used to verify Torricelli's relationship by comparing measured and theoretical value of the velocity. So the speed of efflux V of a fluid through a sharp edge hole at the bottom of the tank filled to a depth h equals to the speed that the body falling freely from a height. In addition, we are not even able to claim that the hole is perfectly circular. There were small jagged edges around the edge of the opening that were a result of a non-perfect tube. Therefore, the velocity of the fluid is too difficult to determine accurately for this experiment, and therefore this aspect of Torricelli's equation should be ignored. Many errors cannot be avoided due to the environment and the instrument used. In conclusion, this lab is thoroughly explored fluid dynamics, designing and conducting an experiment around Torricelli's law for fluids. We have seen how water obeys the law for flow rate changes through different heights. A greater understanding of fluid mechanics have been gained as a result of this lab. In general, this experiment is a great success. given the extremely high levels of accuracy that the data models and the correct interpretation data. Thank you.